Good morning, good afternoon, good evening, depending on where you're joining this live stream from. Thank you for tuning in. My name is Robert, and I've got with me someone in the studio who I will bring on stage very soon. His name is Charles. So, hey, Charles, can you hear me? You're on mute.
Let me unmute myself. How are you doing?
Okay, I'm great. It's good to see you.
Yeah, yeah, good to see you, Kwanadu.
Yes. So, welcome to uh, this presentation. So we'll do it slightly differently. So while I have slides, I'll also try for us to have a conversation so that we can make it more lively. So the interesting thing is we've got two sets of people tuning in. We've got people who are strictly online, and then we've got people at Collab who are having a physical meetup, but they'll also tune in just to catch the talk, and then they will go back to their physical event.
Okay.
Right. Um,
And I also have some students too here.
okay.
Yeah.
Nice. So we can take questions from any side. Any questions that come in as comments, we will see and respond to. Um, And then on your own side, if there are any questions as well, we'll also take them and address them. So I'll get into it. Um, and the talk is about machine learning on embedded systems. But I'll start with machine learning. And interestingly, this particular example is going to turn out to be um, pretty important further down the road. So we all use products that build on machine learning more or less on a daily basis without even thinking about it. And one of my favorite examples is, when you wake up your Android device with the words on the screen. I'm not going to call it out because I don't want any Android devices around me to wake up. But when you wake up an Android device with the words on the screen, and then you go ahead to issue an instruction, such as drive to Murtala Mohammed Square. Interesting thing is, if you've never done it, it's something that actually works. When you do that on a phone, it brings up your maps. So if you're on an Android, it will bring up Google Maps. If you're on an iOS, it depends on what you set as the default, but it will bring up Google Maps and it will give you instructions. Now, clearly, the image that you have on the screen is from a computer, but you get a similar um, result on a device. So this, while it's not advertised as a machine learning product, is made possible by a number of machine learning applications running in the background. And there are lots of other examples of machine learning out there that we use on a daily basis. So recommendations from YouTube, uh, or if you watch Netflix, recommendations on Netflix, but lots and lots of things. When you talk to your phone, you're using machine learning. So, what makes machine learning possible? It's a combination of factors, but it is large amounts of data and it is also um, powerful computers. So, the image that I have on this screen is just representative of a data center. And a lot of the machine learning applications that we use are made possible by these data centers, where you're able to store large amounts of data and you're able to process the large amounts of data in a process called training of machine learning models. Right now, in order to train machine learning models, a number of machine learning frameworks are used. Um, and one popular one is TensorFlow. So we have things like PyTorch as well, which is popular with people in academia, but TensorFlow is the example I'm going to go with. Now, when people hear about TensorFlow and they're not used to the TensorFlow ecosystem, they don't realize that TensorFlow isn't just one thing. Now, I have on the screen examples of certain subsets of TensorFlow. So you've got TensorFlow, which is used for training of models, and it's also used for inference. And this usually requires massive amounts of data and some strong compute. Usually, you'll have some extra hardware that we generally refer to as application-specific integrated circuits. And these could be things like GPUs, graphics processing units, and TPUs, tensor processing units. But we've also got TF Lite. And TF Lite is what you use when you deploy machine learning models onto mobile devices. So if you think of Android and iOS, and you think of a machine learning model, it's typically deployed using TF Lite. TF Lite supports a subset of the APIs that TensorFlow exposes. So not all the operations that TensorFlow supports are supported on TF Lite, but a majority of them are. It doesn't support training, it only supports inference. So you have to use TensorFlow for your model training, and then you'll use TF Lite for your model inference. Now, a smaller set of that is even TF Lite for microcontrollers. So that U there stands for micro. It's the Greek letter mu. So TF Lite for microcontrollers supports a smaller set than TF Lite, and it's meant for use on bare metal or embedded devices. And you will recall that this talk is about machine learning on embedded devices. So we're really going to be talking TF Lite for microcontrollers. So what's a microcontroller? We know what a computer is. Laptops, desktops, those are computers. We can use them for all sorts of things. Word processing, graphics editing, watching movies, even playing games. Those are called general purpose computers. Even your smartphones can be considered general purpose computers. They are not necessarily as powerful as the laptops, but they can do multiple things. So you can read email, compose email, listen to music at the same time. You can play games, watch movies on your smartphone. So those are general purpose computers. A microcontroller, by definition, is a small computer on a metal oxide semiconductor IC. That sounds like a mouthful, but simply put, it's a small computer that is usually meant to do only one thing. So unlike the computer in your phone that can do many things, the microcontroller tends to do only one thing. Now, a lot of the time you interact with microcontrollers as development boards. And on the screen, we have an example of a development board. It's easy to plug into a real computer. But you'll notice it doesn't have a keyboard, it doesn't have a mouse, it doesn't have a screen. It's meant for certain purposes like controlling other microcontrollers, controlling motors. And when you think of motors, yes, actual, electrical motors, brushed, brushless. It's meant for controlling actuators and LEDs. Because there's no keyboard and mouse, it relies on sensors for its own input. And those sensors are connected to the microcontroller via pins. So the gold connectors that you see on this development board are the inputs. They serve as the inputs and they also serve as the outputs. So those ports that are called GPIO ports are multi-purpose. Now, just for you to understand that um, this is actually a computer. On the screen we have the layout of the microcontroller, and you can see the various components. So you can see your RAM there, you can see like your clock generation, you can see your peripherals, and you can see your processors as well. Now, because microcontrollers rely on pins for their input and output, it's important to understand those pins. And so usually microcontrollers come with something that is called a pinout diagram. And the pinout diagram tells you how many pins there are and what you can use them for. These pins tend to support multiple functions. Examples on the screen are, you can see some pins are for power, some pins are for earthing purposes, that's what ground is. Some pins are for general purpose input and output. Some pins are for specific communication protocols. Um, Apologies, Martin. Unfortunately, I've embedded, but I will share a link to the slides at the end. Hold on, I will share that right now. So you'll have the slides. Okay, so feel free to use the slides. You can probably zoom in better on the slides. Right, so moving on, and don't worry too much about the pinout diagram for now. You'll have access to it much later. So moving on, microcontroller development boards, in summary, they make it possible and easy for you to prototype solutions. So they break out the GPIO pins, and then they provide a USB interface. Again, because you don't program directly on the microcontroller, instead you program on a computer. The same way you write code for mobile devices on a computer and then transfer to the mobile device, is the same way that you'll write code on a computer for the microcontroller and then transfer onto the microcontroller. So we're talking microcontrollers. Who makes microcontrollers? Well, lots of companies actually make microcontrollers, and I have a few examples up on the screen. There's a company called BBC Microbit based out of the UK. There's Arduino based out of Italy. There's Sparkfun Electronics, ST Microelectronics based out of France, Nordic Semiconductor, Seed Studios based out of China, Hong Kong. So lots and lots of companies. I haven't listed them. The images are representative of some microcontrollers. On the left side, there are two microcontrollers. The one in a casing with the gold at the bottom is a BBC Microbit. The one on the right, the red, is the bigger one is called a MicroMod machine learning carrier board. And then the smaller piece on the right is the processor. So that's the MicroMod processor. The MicroMod system is a modular system. That's what MicroMod actually stands for. So it's a modular system for controllers that lets you swap out the processors. And I'll get to the point about the processors in just a little bit. And the image on the right, the black case, is an Arduino Potenza H7. And the reason why I have it there is mostly when people think of Arduino, they think of the Arduino Uno. But Arduino makes various microcontrollers. We saw one previously in one of the slides. This is another one. This is the H7. Until a few weeks ago, it was the most powerful microcontroller that Arduino makes, but it's been superseded by another one that we will see shortly. So, where are microcontrollers in use? Interestingly, they're actually in use everywhere. So, if you have any smart devices that are not general purpose computers, they tend to contain microcontrollers in them, even when you don't realize it. So we have microcontrollers in industrial applications, in residential applications, agriculture, robotics. So most people are familiar with robotics. We have them in automotive, we have them in healthcare, wildlife, forestry, smart homes, and in utilities. So on this screen, you just have examples of projects that people are doing as individuals that utilize microcontrollers. But on this screen, they are all projects that specifically embed machine learning into them. So that's just an example of where people are using these things. Now, you've seen the previous examples of microcontrollers, but I wanted to highlight what I mentioned is the most recent addition to the Arduino family, and that's the Potenza X8. It's actually the one at the top. So there are two things on the screen. There's the microcontroller, and then there's a carrier board. And microcontrollers tend to have carrier boards because those boards expose certain things. They expose certain capabilities. The boards themselves, because they are tiny, they tend to not have a lot of space for you to work with. So you'll notice that we've got pinouts to the left and to the right, but how many things can you connect to those pins? But when you have a carrier board, such as this Potenza carrier, you then expose additional things. And you'll see, for instance, that this carrier to the front, you can already see that there's an Ethernet port. You can see two standard USB ports. You can see a power input. And then you tend to have a whole host of other things. Now, in terms of microcontrollers, all of the microcontrollers I've shown here are built on technology from a company called ARM Holdings, which is a UK company. And they all support machine learning. So they're built from the ground up to support machine learning. Or, well, yeah, I don't want to say that the machine learning was specifically built for them, but the TensorFlow Lite for microcontrollers specifically works on the technology from ARM. Now, ARM itself produces three types of processor technology: the ones in red, the ones in orange, and then the ones in blue. You can ignore the ones in yellow. They're kind of phased out, they're classic. So microcontrollers utilize processors in the blue region. And so those processors are called Cortex-M processors. And the orange ones are real-time processors. So you find them where you need to have real-time clocks in operation, such as in automotive applications. And then the ones in red are for more application intensive operations. So you'll find them in things like single board computers, general purpose computers as well. So if you're conversant with the Raspberry Pi, depending on the generation, uses something like a Cortex A72 or an A57. But we're going to be focused mostly on the Cortex-M. And there are various Cortex-M processors out there. So what's the difference? The difference is in something called the instruction set architecture. Again, don't worry if this isn't too clear. When you have the slides, you'll see it closer. But basically, what you then see here is another image of subsets and instruction sets. So, long story short, different Cortex M processors have different sets of instructions that they support. And the instruction is simply one command that lets you get something done. My favorite example of that is a square root operation. If a processor natively supports the square root operation, then you can get that done in one clock cycle. But if it doesn't, then you'll need to natively implement your own algorithm because the processor doesn't support it. So it doesn't mean you can't compute the square root. It just means that you need to know the algorithm for doing that. Now, why would the processor choose to not support certain instruction sets? Well, size, cost, power requirements, those sorts of things. So there are situations in which you know that you're not going to be doing certain types of computation and you don't need to spend more money getting a processor that supports all of that. So when you understand that instruction set hierarchy, you then understand why you have different processors and why some processors natively support some things and some don't. So the point here is that I recently saw a comparison between a Cortex M0 and an expressive microcontroller where they were trying to make them generate some Mandelbrot images. And I found that to just be funny because, well, if you're just looking for views, then it's fine. But if you know what it is that you're comparing, you start to ask yourself, am I comparing apples to oranges? Particularly because a lot of, in fact, the Cortex M0 and M0 Plus do not support floating point arithmetic. Right? But there are lots and lots of things that you can do without supporting floating point arithmetic. Case in point is if you are reading sensor values like temperature and humidity to then make certain choices as to whether to do some things. For example, if you use a microcontroller with temperature and humidity to maintain a chicken coop, for instance, to maintain a large scale operation for chickens, you want to keep their interior environment within certain temperature bounds. So all you need to do is say, if the temperature and humidity get too high, open some vents to let fresh air in. And if it gets too low or if it's getting dark, shut the vents. So you don't need to do any sort of computation. All you need to do is read and operate, and that sort of thing. So this is it with instruction sets and understanding the various Cortex processors. Because next, when we start to talk about the microcontrollers, we're going to be mentioning what Cortex processor they have, and then it starts to make sense. In simple terms, the larger the number, the greater the support for instruction sets and the more powerful the processor is. So for example, your Cortex M0 Plus will tend to be the least powerful processor in some cases, and then your Cortex M4 will be more powerful than your Cortex M0 Plus. Then there's an M4F, and the F means that you now have support for floating point arithmetic. And then you have your Cortex M7, and then there are some other ones like the M33 and the M55. Right. Now, we've mentioned that TensorFlow is what you need to train machine learning models, and TensorFlow Lite for microcontrollers is what you need for inference on microcontrollers. But what does it take to actually put a machine learning model onto a microcontroller? It takes three things basically: an understanding of electronics, not that the machine learning model itself is utilizing electronics, but an understanding of it in the broader sense of the circuit that you're going to be dealing with, because usually the microcontroller doesn't stand on its own. So a general understanding of electronics, an understanding of software, because you're programming the microcontroller. Usually this tends to be in C, but in more recent times, there are microcontrollers that support other languages besides C. And then machine learning, because you can't do um, machine learning without machine learning. So three things in general are required. And so to program microcontrollers, you need to know C or C++, or depending on the board, you need to know MicroPython. So the board that I showed with the pinout, which is Raspberry Pi Pico, supports MicroPython. To the right of the screen, you see something called Spresence, and Spresence is from Sony, and it supports embedded Java as well as C and C++. Um, so I mentioned earlier, you need to understand electronic circuits. You need to read documentation. So I'm aware that sometimes people want to be software engineers, but they're averse to reading documentation. It doesn't exactly work the same way in electronics and the embedded space. You have to read documentation. If you don't, you're just going to blow up your equipment and spend a lot of money. You also need to read specifications, different from documentation, of course. And then you need to learn how to read schematics. Schematics is how electronics engineers communicate their networks of connected devices. And then lastly, you just need to love making things. Right. So what does it take to then deploy a TensorFlow Lite for microcontrollers model onto a microcontroller? Well, first you need to train your model, and that requires collecting data, labeling data, and then training the model. Then you need to convert your your TensorFlow model, which is going to be in a proto buffer format, to a TensorFlow Lite flat buffer. But that just takes it to the point where you can put it on the phone. It's not ready to go on the microcontroller yet because it's too large. Microcontrollers don't have that much memory. So now you need to perform quantization. And quantization takes you from floating point to integer arithmetic. And that's why you can do this on boards that don't support floating point arithmetic. Then you need to write an embedded program, and then you need to transfer your model into that program. And then you need to implement any additional requirements that are specific to your board, and then compile and build, and then flash the resulting firmware onto your microcontroller. Just talking about it sounds like a lot, and it usually is a lot, because we're going to be going back to say, learn C, learn Python, learn TensorFlow, learn this, learn that. Lots of specializations that need to be acquired before you even get to the point of deploying to a microcontroller. However, we're in the age of democratization. So we're talking about how do you make things easy for people to do. And so we see that with lots and lots of courses that are saying, hey, you don't need a PhD to train a machine learning model. Here's how to train a machine learning model. Some of them even automate it. So things like AutoML on Google Cloud Platform show you how to train a model. Just bring your data, bring your labeling. It will find the optimal model for you using neural architecture search. So Edge Impulse makes that possible in a similar manner for embedded devices. And so I'm just going to walk through some screens that show an example of using Edge Impulse to train your machine learning model and deploy to microcontrollers. Now, this doesn't mean that you shouldn't know anything about machine learning. In fact, as we move further, you'll see that having a knowledge of machine learning helps you be successful in training these models. But at the end, we're also going to highlight certain courses that are available for you to take, and also mention some support that is available in that regard. So on the screen, what you have is your Edge Impulse project. So Edge Impulse works with projects, and the example I'm showing here is I'm training a model to detect whether or not someone is saying either yes or no, and that is called wake word detection. So if you go back to the beginning where I showed an example of waking your phone up and telling it to show you how to get somewhere, you know, it will launch Google Maps. So it's two things that are happening there. The activation words, the pair of words that activate your Android device, that's called wake word detection. And so here you could replace yes with that wake word, and you would be training your own model to do that. There's something that happens. So there's some sort of pipelining where when the device wakes up in the context of the Android device, when it wakes up, it starts listening for additional instructions. So that second line in my example, when I said drive to Murtala Mohammed Square, it would take that and pass that to a bigger model. So there are actually two different models in operation here. There's a wake word detection model, and then there's a natural language model that does a just a speech to text conversion, and then it passes it into a separate model to interpret what that thing is doing. So there's a whole bunch of stuff going on in the machine learning domain. So here, the slides will show you how to do that on Edge Impulse. So the first thing that you want to do is data acquisition. And so just a second. Okay. So the first thing you want to do is data acquisition. And you're able to do that on Edge Impulse directly. You're able to connect a device, such as a phone, and use that to record sounds, or you're able to upload a folder with recorded sounds. And once you do that, you see here that you're able to even listen to the sound. You're able to see the waveform of that sound, and you're able to process it. You're able to split your data into training and validation data sets. So the entire machine learning pipeline is available to you. Now, once you're done with collecting your data and labeling your data, so the second column in the collected data section just shows you the data labels. Because this is a classification model, you're going to need to have labels in there. Now, once you've collected your data, you can go ahead and create what is called an impulse. An impulse is simply just a pipeline. And what you see here is, if you have any experience with speech or natural language, it's the first thing that we're going to do is we're going to process the data. And so that's the white box that you see there with the title Audio MFCC. MFCC stands for Mel Frequency Cepstral Coefficients. And so what we're saying here is implement a pipeline that will perform feature extraction, and the end result will be Mel Frequency Cepstral Coefficients. And then you're going to add a block that performs classification using a Keras model. So Keras is an API. It's a TensorFlow API. Now, even without knowing Keras, if you know what machine learning is, if you know what layers are, you'll be able to work with this. And then the final in green is your output features. So we can go in now and look at here. This is where we process the data and extract the MFCCs. So at the top, you can see your raw data, similar to what you saw during data collection. At the bottom, you can see all of the parameters for MFCC extraction. Edge Impulse will give you defaults, and if you don't know anything about it, you can just leave it alone. To the right, we've got the result of our processing to MFCCs. So this is called a digital signal processing result. And so what you have here is a visual representation. So this kind of takes you from a speech domain to a computer vision domain. The only difference here is that you're not dealing with a two-dimensional image, you're dealing with a one-dimensional image. So you shouldn't process rows and columns, you should only process columns. So moving forward, once you have your MFCCs, you can then define your ML model. And so this is your Keras model. At the top, we can see certain parameters. And so this is again why you need to have an idea of what it is that you're doing, because you see, it's asking you for things like number of training cycles, your learning rate. So if you don't know what a learning rate is, you can't really get past this. What's your validation data size? Do you want to perform any sort of data augmentation, for instance? Those sorts of questions are things that you need to answer. At the bottom, while it doesn't look like an ML model, it is an ML model. So if you look closely, you'll see that you've got like an input layer, and you've got a convolution layer somewhere there. There's a reshape, and then all the way down to your output layer. To the right, you can see, because I'm done training the model, you can see your model output. You can see what the accuracy looks like. You can see what the loss looks like. There's a confusion matrix on the screen for the various classes. There's even a visualization that shows you what instances were classified correctly, what instances were classified wrongly, and then additional data at the bottom. Now, if you've got experience with TensorFlow, you can actually go in and edit the code yourself, and that's called expert mode. And you can see that the very first line there is importing TensorFlow as TF. You can take your time and read through the rest of the code once you have your hands on the slide. So once you're done training your model, you can deploy to various microcontrollers. You can export an Arduino library. You can export a C library. If you work with the NVIDIA Jetson, for instance, you can export a library that supports that. But you can also see various microcontrollers on the screen. So depending on what your use case is, you can deploy directly to the microcontrollers. Again, you can also collect data directly from these microcontrollers, which is usually the best thing. For example, if you're going to be training a model to detect abnormal vibrations on machinery, then you're going to want to collect the vibration data directly from the microcontroller that you'll be using in the end result. And all of that is something that you can do from the devices section of Edge Impulse. So there's a whole lot more to microcontrollers and machine learning on microcontrollers that goes beyond my presentation. There's only so much I can sit down here and talk about. But you can check out the ARM website to learn more about the ARM microcontrollers. You can check out Edge Impulse to get started with what they're doing. You can visit the Tiny Machine Learning Foundation. They hold all sorts of webinars on a weekly basis. The microprocessors that I mentioned, the M0 Plus, Cortex M0 Plus, implemented in the form of an RP2040 from Raspberry Pi. And there's a link to TensorFlow Lite for the RP2040 that you can go and check out. And then on the right, there are a bunch of courses and specializations that you can take. What I will do is I'll send out a bunch of emails to participants. And if you're interested in any of these, I will tell you what you need to do. And once you hit a certain milestone, I will send you a development board. The development boards are a bit hard to come by right now, but you can start courses without the boards, and then you can get to a certain point where you'll then need to use the board. So if you're serious about it, I'll make boards available, whichever course it is you're taking. So you can take the Tiny ML specialization or the Edge Impulse specialization. For those, you'll need an RP2040 board, such as the Arduino Nano RP2040 Connect, which I will send to you if you send me proof that you're taking the courses. You can take the Embedded Systems Essentials with ARM course, or the Build Your First IoT Application with ARM course. Those require an embed device. While the RP2040 will do, I will send you a different evaluation board for that purpose. So thank you we've come to the end. I will once again paste the link to the slides, and then I'm open to take questions. So please feel free to type any questions that you have into the chat. So the courses, you can take the tiny ML specialization is on edX, embedded systems essentials is on edX, and build your first IoT applications on edX. All of them are free to take, so you don't need to pay for the certificate. The Edge Impulse course is on Coursera, and I think you can enroll for free. I think you can even take it in its entirety for free. I've seen that mentioned. So yes, you can take all of them without having to worry about payments. Okay. Any more questions? So I have a question from someone who says, what's the advice for people who don't have an electronics background? So the okay, before I answer that, so there's someone watching along on Facebook who says, where can I get the link for the slide? I think I will just log on to Facebook and paste that link right away. So give me a second. So advice for people without an electronics background is take it slow. So I also do not have an electronics background. I come from a computer science background. What you can do is just take one of the courses, whichever one you're interested in, start with that. When you're done and you're building products that are very specific to what you've learned, you can then ask yourself additional questions. And those questions are going to be how would I or what do I need to know? Like, how does this thing work, right? So, for example, you know that you've got your pin-out diagrams, but those pins, you might be told that they connect to like an LED to flash an indication. But then you're told that your LED must have a resistor attached to it to avoid sending excess current. So you can then say, okay, what's going on here? Why do I need to do all of this? And is there a simple book that I can read that explains all of this? And the good thing is that there are books. I, for instance, picked up a book called Electronics for Beginners, and it explains all of these concepts from the ground up. But it's a gradual journey, so it's not something that you're going to try and short circuit. It's not something that you're going to say, "Oh, I'm going to master everything in 1 month or 2 months." Don't go with all of those Instagram celebrity stories. Give yourself time to learn things. Anything that is worthwhile is worth learning at a gradual pace. So, okay.
Yeah,
So,
hello.
yes.
Sorry, some of my students came late, so I'm just trying to get them set up. They are going to catch the conversation on YouTube later on, but probably you see some of them posting some questions on the YouTube chat group. We'll try as much as possible to answer as many as possible. Some are actually very interested in the courses and specializations that you mentioned. We'll try and see that the community here in AFI will get the serious ones. We'll push them and see how we can make them make some progress as regards that. So some of them will be asking some questions on their YouTube. So the ones we can answer, fine. The ones we cannot, and reschedule some other day, fine. Thank you.
Okay, thank you for that. So I have a question from Daniel, and he says, which board do you recommend for beginners when starting embedded system? The board I recommend is um, the Raspberry Pi Pico. I will drop a link here. Um, I recommend the Raspberry Pi Pico, and one of the variants is the Arduino Nano RP2040 Connect, and I'll also drop a link here for that. So either one of those two boards that you can get your hands on are lovely. But what I'll also say is if you sign up for one of the courses, so I will drop instructions. If you sign up and you do what I say, I will send you a board. Okay, so those are the two links to the boards. All right. I think I have another question here that says, I want to build a computer vision project like face recognition IoT device. Um, so it's asking whether you have to use something like a Raspberry Pi 4 or the NVIDIA Jetson board. So it depends on what it is you're trying to do. So boards like the Portenta will do facial, well, they will identify a face. So you're able to run a model that will tell you that there's a human being. And the way to know that there's a human being is to identify the face. And you can identify a face and draw a bounding box. The frame rate is not the best. So what that means is that it's not going to be doing it at 30 frames per second type thing. But you can run it. So anything that has a Cortex M4 and above will do that for you. The bigger consideration is what sort of camera you have that is going to take the image and do the processing. Of course, the Raspberry Pi 4 will process at a much faster rate. And then you can get like a camera case. So if you have a Raspberry Pi 4, unfortunately, they are pretty scarce right now. But if you can get your hands on a Raspberry Pi 4 and a Raspberry Pi camera and you have a Pi case, you can also build a solution that does that. So it's more a question of how many frames you need to process per second, how quickly you need your embedded solution to work. The good thing with the Raspberry Pi 4 is that you can still use it in a deeply embedded manner. It also has its pins broken out, so you can still connect sensors, you can still operate actuators and do all sorts of things. So if you're thinking of something that says detects a face and then enables something, like if there's someone in the room, if you see someone walking into the room, turn on the lights, turn on the AC, and do all sorts of things. And then when the person walks out, you can shut it down. You can do that, or even more esoteric applications like if someone walks into an elevator, are they putting on a face mask or not? If they're not putting on a face mask, the elevator doesn't work. If they put on a face mask, then it works, type things. Um, so I have another question that says, how can one start embedded systems from scratch? So from scratch, it would be take the embedded systems essentials with ARM or build your first IoT application with ARM. Those are uh, from scratch courses. There's also a book actually, and I think that this applies to a whole lot of people. Um, if I can find it, I usually have a short. So the book is getting started with MicroPython, uh, and it works well with the RP2040. It's actually aimed at the Raspberry Pi Pico. Um, so just a second while I find that book. So I'm just logging onto the website to bring up the book. If I can find it here. Now, interestingly, I also tweet about the book pretty frequently. So if you follow me on, yeah, well, I found the book. Just a second. Actually, I will just drop this link. It has a whole lot of books in there that you can get. So even for people asking about computer vision applications, there's a Raspberry Pi camera guide there that you'll find to be useful. Um, and then for those who need to get started with C, there's also a book there as well. Um, okay, so yeah, you'll find a bunch of useful books in there. I don't want to take too much time digging through the documentation. So, for someone building a smart learning platform for various fields, what approach in ML would you apply? I can't answer that in one sentence. So, ML as a field itself is very wide. While there are some simple things that you can do with one model, a lot of things require a whole pipeline of models to get things done. So, unfortunately, there isn't a single answer to that. It's almost like asking what approach would you apply if you wanted to build a car as a mechanical engineer. I'm sure it's not a single sentence response. Okay, so we are almost at the end. I will take any final questions, um, and then I will set people free. Okay, hi Raji. Olaoluwa. Okay, so I'm counting down to ending the broadcast in 60 seconds, unless any additional questions come in. So I should also mention finally that there's a Twitter community that I set up, and you can join, communicate, ask questions, that sort of thing. So here's a link to it. So another question from Facebook says, for someone coming from software development background, what is the next thing you'll recommend to study for getting into embedded systems? So I would say pick up the getting started with MicroPython book. That's what you really need. Getting started with MicroPython. Um, and let's see if I'll find a quick link to it. I know I usually talk about it. Um, I might have to go way back to find it. Okay. I'll tweet about it again. So just keep an eye on my Twitter handle, so I don't waste too much time. Um,
Can you drop your Twitter handle so we can? Okay. Okay.
yeah,
Yes. Okay. The link is up there. Okay.
yeah, it's up there, but I'm doing that now. So materials on electronics. So like I mentioned, the book that I recommend is Electronics for Beginners. It's a um, very good book. That's the book that I would recommend. There's a bunch of other books as well, but I also find that structured learning is important, and people just tend to read too many things simultaneously and get confused. Um, so if you want to read about Electronics for Beginners is a good one. And if you are coming from a software background, then getting started with MicroPython is a good book. I'm just scrolling down to see if I'll find where I pasted the last link to it, but the link to the books as well will take you there. But I just want to have one very specific um, link. I'm surprised I can't find it in my posts. Um, okay, well, I can't find it, so I'll just leave it. All right. Yeah, so Tunji, just get the slides. The slides are what you need, and I'll paste the link to the slides again. Okay, so our time is up. Thank you, everyone, for tuning in. And please keep the conversation going on Twitter. Join the Twitter community. Let's keep talking and chatting and asking and answering questions. So enjoy the rest of your day. Thank you.